Okay. I've started recording, so if 5 people are not there, I can watch it later maybe. Okay. I think this is where I stopped last week. Uh, we were talking about all the different types of fatigue in terms of ductile materials. What are the issues that you're gonna have? What are the variables that can be there, which causes the failure to happen way earlier than what is expected, and all those different things. Like a brief introduction. So this is the type how loading generally happens in materials. They are not going to be uniformly or constant amplitude loading, which is the one over here, where you have a constant load happening, where you have I don't know whether I did this part even. Okay, I'll just start from here. A constant amplitude uh, loading. There are a fixed load range, which is max minus min. A fixed one. This is all fixed. If the load rate is fixed, your amplitude is also fixed. Stress ratio is also fixed. R is equal to min by max is also fixed. Mean is fixed, which is min plus max by 2. So all of these values are fixed in the testing. So for these kind of testing, all you actually enter is just your min and max value. Sorry, um, your amplitude and mean value. So that's the only two information that you enter into the machine, because mean is equal to max plus min, while amplitude is max minus min. So once you have these two values, you can find out what your max and min is. So you can find out what your load ratio is going to be and all the other numbers that we need for fatigue. So that's the reason why you enter just max and min, sorry, amplitude and mean. You can figure out all the different things that is needed for a fatigue test. Um, it is the best way to run a lab experiment ways. It's the easiest way to run a lab experiment. Most of the fatigue data that you have is based out of constant amplitude testing. When you have complete reversal, which is load R is equal to -1, load ratio is -1. So let's say you're going to 1000 MPa on the positives, you're going to -1000 in the negative. So there are major advantages of this and disadvantages of it. But in the hindsight, every cycle you're going past zero. So that's something that can create crack closure effects in the material. And also, every time you load the material, you're actually opening up the crack again after crack initiation, that you can the environment can directly impact the crack growth in the material. Um, Zero or a full tensile load is basically every cycle you go to zero. So you load, unload, load, unload, load, unload, load, unload for a long period of time. And that's one kind. The other one is being completely tension load. Most of the testing that you do uh, in terms of test results and any kind of application that we do are generally some version of tensile loading. It can, most of that is point one is the worst kind of tensile loading, because the stress range is from 90% is the stress range for those materials. So it's the worst condition, but if you can do a point 0.5 load ratio and stuff like that. So these are constant amplitude, and this is how you fill up all the material properties or material data books in terms of fatigue properties for materials. The only thing that you have to remember is if you change the heat treat, or if you change the processing technique, or change anything, you have to do all these ratios in terms of fatigue properties again for that set of materials. So in terms of variable loading, this is generally how all the test loading is going to happen. Variable loading is how you want all your um, any structure that you take is not going to have 100% of the loading at the same rate all the time. Um, Even if you take a car, if you take anything that you use on a day-to-day basis, there are times when you're going to use it in a normal way. There are like take a car. When you are in a city, you're going to use your brakes, you're going to stop, restart, all those different things. But when you are in a highway, you're going to be in a cruising altitude, cruising velocity or speed. And then again, you go back to a more traffic area, you're going to be like going in a constant speed but at a different speed. So there's a lot of variability that happens with just a car. Same thing happens with a ship, same thing happened with a plane. uh, these things are even bridges. Bridges are going to be, let's say we have a bridge in, like if you are in Pittsburgh, a bridge which is taking you inside the city and outside. The going inside the city bridge is going to be really busy at mornings from 7 to 9, while the bridge which is going outside is going to be really busy from 4 to 6. So at the other times, both bridges are going to have a decent amount of crowd, but not as much as they're going to have in those 2 hours brackets. So that's how the variable loading works, and we want to make sure that the maximum load that happens in the variable loading is way below the constant amplitude loading strength of that material. So that's the major thing that you have to see. So the variable loading, let's say for 10 million cycles, which is the endurance limit of the material, for 10 million cycles, you have to load the material at 600 MPa. You have to make sure that the stress in that bridge for variable loading at the peak hour should be way less than 400 MPa. 400 to 500 MPa. That's what you have to make sure. Since it's all in stresses, the biggest way you can change it is making it bulkier, or make sure that you have enough material to withstand all the sudden loading that you have, or to distribute the load that you have in the material in the system. Uh, there are a lot of models, mathematical models, which predict all these things, but it's very difficult to exactly predict the failure of a bridge or anything. But if you can maintain the stress way lower than the maximum stress that gave you 10 million cycles, you can at least hope that the material will survive for a long period of time. Uh, there are bridges in the 50s and 40s which, because of heavy wind, was just crushed and failed. Probably a week after it was opened, it failed in a week, and there are videos of it happening. I think it's in Wisconsin. I think the one that failed. Uh, and those things happen a lot. They used to happen a lot before. Nowadays it don't much. uh, but the reason why they happened a lot is because they were not taking into consideration all the variable loading that was happening to the bridge, which is basically the environment, the wind that was happening, the temperature that was happening, and also different connections that you had in a bridge. And all these things were the reasons why it failed. Let me see whether I can find that video online. Just stay there. I'm sorry, it was actually um, the failure that was happening in Washington, not Wisconsin. But this was like 1940s, where they didn't have much of any research into um, fatigue. That was the major problem that they were having, is because they didn't do much of any studies into fatigue. Let me see. Don't think the audio is needed because it's very clear how it fails. They set it up. It was like a few $1 million bridge, and you can see how badly it was swaying because of the wind, and it was a complete failure, and it broke and fell within a week of erection of the or opening up of the wind. Oh, sorry, of the bridge. And all this is because they were not taking into consideration of the variable loading that can happen on a structure. Uh, there's similar things happen to buildings too at a point, but buildings at least had the failures were not that much, but there was failures that was happening in a few countries where they were building it way more than what is supposed to be, and not taking into consideration all the skyscrapers. The major issue is not just the foundation, but is also the wind that is going to have. Higher the area, more the wind contact, more the sway that you're going to have. And that sway for a naked eye could be nothing, that you don't see anything happening. But with time, if it's a windy area, there's every chance of that wind destroying the building. So that happens a lot when you have a lot of skyscrapers in the city. Uh, So, characteristics of a fatigue crack. This is where we're going to start learning how fatigue crack initiates, what is the reason why it grows, and all those different things. Um, so let's say this is the material with several grains like this. Just looking at a small region of a material, and I'm fatiguing it. Doesn't matter what condition, but let's say I'm fatiguing it. The minute I start fatiguing, and depending on what kind of material and all those things and what stress, you are going to generate voids and at different areas, because you're starting to have dislocations created in different grains. So all the dislocation, what it means is like you are displacing an atomic position from point A to point B, and thereby creating a void over there of atoms. And that void is going to be really small as you keep loading it. Two of the voids will try joining to each other to form couple of voids have to join together to form a small mini crack that happens in the material. And these mini cracks are generated after that at thousand different places. So all these mini cracks are not going to do much to the failure of the material until a surface crack starts, which is going to be the major crack which forms, because all fatigue cracks starts from the surface. So once a fatigue crack starts from the surface, all these mini cracks or this crack is going to grow in the direction of shear plane or in the direction of dislocation, which is basically going to be the 45-degree angle. And thus, once that happens, all these voids and small cracks that is generated within the grade tries to join with the major crack and basically try growing to failure like this. So there are two things that happens. One, surface crack is generated, which is going to create your major crack in the material. And second, all these voids and small cracks that is generated within the material are going to join together in the direction of uh, a dislocation or shear plane, and that's going to be this plane at which your crack is going to propagate and reach failure. So every time what happens is once there is a crack generated, let's say there's a crack like this, there is a plastic zone that is generated at the edge of this crack zone over here, and the plastic zone grows in terms of a kidney bean. And the reason why this plastic zone is more than any other region, all other region over here in the material are all in elastic limit. But at this point, since the area of that crack tip is so small for the stress that is applied or the load that is applied, load divided by the small area is going to give you a stress which is way higher than the yield stress of the material. So this area is going to have a plastic zone keep going. And once the plastic zone goes beyond the um, a certain stress, then you're going to have a generation of a smaller crack or propagation of the crack. And after that, you're going to have more plastic zone generated, and the plastic zone is going to grow until it reaches another size, and then you're going to have a crack growth. And all this takes a long period of time to happen, and all this happens because there is cyclic plastic deformation that happens in the wake of the crack or in the front of the crack, while the rest of the material are still in elastic region. So no matter if you have hundreds of these small cracks or thousands of these small cracks created, it's only the major crack is which is going to propagate and lead to failure. So the major thing that you can do is, let's say I have the same thing and I have minor cracks at 100,000 places. But if my surface is smooth and polished, I'm not going to generate a surface crack at all. So the material, even though it has hundreds and thousands of small micro cracks within the material, since I don't have a crack initiation at the surface, the material will still survive. But the only major disadvantage of this is once a crack initiates, from that point to propagation to failure would be only a few thousand cycles, before which it starts initiating to failure will happen and the material will fail. And that's the only disadvantage of this. But in terms of any fatigue applications, if you see it, the surface would they make sure that the surface is all polished, that there is no any surface roughness in the material, because any surface roughness in the material is like a stress razor or a stress concentration or a point at which the crack can initiate in the material. But if you make sure that the surface is smoothened, then you are reducing the chance of a surface crack to initiate in the material and grow into a major uh, crack. So, in conclusion, in ductile solids, the crack initiates along the plane of maximum shear, or in the basically in the direction of shear plane or slip plane. The stress risers can occur at various positions on the free surface, resulting in initiation of many cracks in the material. The stress risers, what they mean by that is because of how the crack ends, or crack is initiated within the material in 100 different places. Every time you cycle, the edge of the crack or the wake of the crack can grow a little bit more, and thus making it a stress riser or a stress concentration within the material. So the microscopic cracks that is generated in a thousand different places within the material, they all grow at different rates. And the reason for that is every grain, as we talked about this before, is oriented in a different way to the direction of loading. And because of this um, difference in the grain position with the loading direction, there is every chance of you having different rate at which the crack growing at different spaces. And that's the reason why it takes a long period of time before one crack becomes the major crack for it to start growing. So the crack initiation part can happen pretty soon in the material. Within the first 1,000 material cycles, you can have all the cracks initiated in the material. But for you to have a major crack growing in the material, it might take even millions of cycles. Anything above 10,000 to about million cycles for the major crack to be formed, and then you have slow crack growth, and then it leads to failure. So all these things can take a long period of time, depending on how the grain boundaries are, what are the sizes of the grain boundaries, and number of grains that you have. Because every end of every grain boundary is basically a door that you have to break out of and go to the um, next grain. So basically, think of cracks being a SWAT policeman that they have to break into all the rooms every time they hit a deadline. Every time they hit a door, they have to break that open and go to the another one. So they have to apply a higher stress. So you have stress raises at every point and slowing down the rate at which the crack is growing. So all these things takes a long period of time for it to happen. Uh, so load distribution in terms of a 3 point bending or 3 point loading that is happening in the material, can you are in if you remember if you guys know what a 3 point bending is, let me explain that. So let's say 3 point bending is a test like this where it's held in 2 points like this and you're applying a stress in the middle of the material. So what is the issue with this is in this kind of a testing it is a little different because you are actually forcing or applying a load at a single point and making what to say deformation start at that point over here. And since that area of contact is very low and the load that you're applying is higher, plastic deformation starts happening at that region. The reason why the load is or the crack growth is controlled is because you have two types of loading that is happening. The bottom part of the material is undergoing tensile loading, while the top part is up taking it's undergoing compression loading. So there's two types of loading happening which is canceling each other, but you know that the cracking is going to start because of the way it is. It's going to start somewhere over here after this tensile loading reaches a particular plastic deformation, that the crack would start from the center spot where it's the load is being applied opposite to it, and then the crack would grow along and reach failure like that. So in a 3 point loading, depending on the load distribution that you have, you are localizing the area at which the crack is going to initiate and propagate and go to failure. And most of the time, what if it's a ductile material, your crack is going to start on the opposite side where extension is going on, and then basically grow upwards to failure. Uh, and if you are having a brittle material, it's going to be a little difficult. In terms of brittle material, the crack would start growing on the point at which you're applying a load, and then just grow towards failure or towards the end of the material. So that's basically how it works. In most structural components, the fatigue cracks initiates as from a stress riser. So even if it fails on a surface, if you, I don't know whether you guys have seen this happen when you have a plain material and you know that there is fatigue happening on it for a long period of time. Let's say you have a fatigue test that's running on a material for a long period of time. I don't know whether I can. I have a sample with me. Yes. Okay. Let me start my video for a second. Okay, I guess you guys can see me right now. So let's say this is the fatigue sample that I have. Okay, this is an aluminum. Uh, it's a metal matrix composite, so it has 20% silicon carbide in it, and it's a 22 series aluminum alloy. So it has copper in it and aluminum in it, and also it has 20% of silicon carbide to make it harder. So let's say this material. So if I fatigue it like this for a long period of time, let's say at a stress which is very low, at about 10 to 100,000 cycles, 200,000 cycles, I would start seeing the surface, even though it's, if you can see over here, it is as smooth as possible right now. Uh, but after cycling it for 100,000 cycles or 200,000 cycles, the same surface is going to have some lines that I can physically feel. Okay. And the reason why that happens is because of the dislocation movement and all those things. You will start, I'll talk about this later in detail, but you will see some lines that is found on the surface and you can actually feel it. And because of those feeling that you're going to have all this stress raises or the dislocation that you see on the surface, your roughness of the material starts going up. Once the roughness of the material starts going up, that would be the stress raiser, which is causing a stress concentration because of all the roughness that you have, that is going to cause a surface crack, and that crack is going to, that's how it kind of grows. Um, so when you have a, let's say, let me close this video. Let's say I have a welded component. Then in a welded component, that doesn't matter much. Okay, there are two reasons why a welding component would fail in fatigue. One, basically, the weld point is going to create a surface roughness in the material, and that surface roughness becomes the reason why surface crack is initiated from that point. The other reason is the way you build the material. Let's say you have gas pockets and all the other issues that you can have from welding, and you didn't clean the weld after it's done, or and also do a heat treat after it's done, then all these reasons are going to make it a point where there's going to be a stress raiser at that gas porosity area where your failure or your crack is going to start. Uh, So the stress raises could be anything. It could be just the surface roughness because of the way it was made. Let's say I'm rolling the material. Every time I roll the material, I can have some form of a surface roughness that I can create. Let's say I'm forging it, that will create some surface. No matter what I do, until I do some grinding and cleaning of surfaces, I am going to create some form of a surface roughness in the material, and the place where you have the highest point in your surface roughness is going to become the stress raiser where the surface crack can start. Uh, but all these things are in a environment where you believe that the only worst thing that causing the failure or cracking is the stress applied. But when I keep adding all the temperature effects, the residual stresses in the material, which is due to any processing that I do, all the residual stress on the surface that I can have, those reasons, and also the environment, all these things are going to change the rate at which the crack is initiated and propagates in the material. So there are 100 reasons why um, a crack can initiate and grow, but every reasons can be given an explanation, and no matter what is the reason, uh, 90% of the time the crack is going to start from the surface because of a stress raiser. Doesn't matter how the stress raiser was formed, but it will start from the surface because of a stress raiser. The 10% that I said, which is not starting on the surface, are the reasons why. Let's say I'm making a 3D printed metal. Uh, the way 3D printed metals work is basically you have powder bed, a bed of metal powder, and I'm applying laser or any other heat source to fuse them together for a small layer, and then I'm gonna build another layer on top, build another layer on top, and keep going like this. So the major disadvantage of advantage and disadvantage of this process is advantages. If I have the money, I can control the rate at which I'm building the material and also make sure that the fusion is pretty good. The disadvantage is, let's say I don't have a fusion point happening at a certain point, and I have a huge void in that material even before I start loading. Uh, the cracking would be starting around this void or huge material. Let's say I have a gas entrapment or a huge void or a particle of a foreign material just added to it by mistake. Whatever the case is, I would have a start initiate big crack starting from that huge foreign particle or void in the material, and thereby that becoming the major crack and growing outwards. And this could be attributed to like 5% or 10% of the failures that happens in metals. Uh, but in most cases, failures in metals start from the surface. When you come to composites, it's a little different because a composite is made out of your matrix and your um, fibers. So you have your our additives, and because you have like that, and the two of them can be two different materials even. There are issues that will happen because of the fusion of these two materials or two different types of material that you have. It could be the reason why the cracking starts on the inside of the material. And also till date, even though CMCs has been there for like 2 decades right now, CMCs is just ceramic matrix composites. Till date, a material with zero voids is very difficult to create in terms of a CMC material. So you have to have expect voids to be present in the material. The only thing that you can do nowadays is like you can make sure that the size of the void is not huge enough that a crack would initiate from that point. But other than that, you would know that in terms of composite, the failures the percentage of failures happening from to start from the inside of the material increases from 10% to about 30 to 40%. But still, major cracks would start from the surface. So, stress life approach to fatigue. This is if you remember the first chapter that we saw, this is the SN curve method to fatigue. In SN curve method, the only major thing that you have to worry about is your stress amplitude, which is basically your maximum stress minus minimum stress applied to material divided by 2. That's the major way by which you're going to compare all the properties of the material. The best way to look at this is applying, let's say, a material has an 800 MPa yield strength. So once the has an 800 MPa yield strength, you start testing it in fatigue with a maximum stress of 750 MPa. Uh, Let me see whether I can. If you guys are working on fatigue, I can always help you guys by I even have an Excel sheet generated. Let me see whether I can find the Excel sheet. Uh, Used to. Let's see. It's just a fatigue test data point. So, so this is a fatigue test sheet that I make for every material that I ever test. So the only inputs that I have to give in this. test is I have to give a multiple test data points of how many tensile tests that I do, and then it gets the average of that and puts that value over here. And the other one that I have to give you is how what's the diameter of a round sample that I'm using. If I'm not using a round sample, if I'm doing a flat sample, I can directly write what the area is. And once I have that, it generates this whole curve for me, or set for me, where I can go from 92% of its yield strength to about 20% of its yield strength, and then I'll get all the values that I need. I'll get the minimum stress, maximum stress, amplitude, mean, everything that I need to enter into the fatigue test so that it can run smoothly for me. So how I do fatigue test is I'll do initially at around 90%, and I'll see what the life of the material is. Let's say the life of the material is only 8,000 cycles or 6,000 cycles, then I would go even lower and do like 85% of the test or 80% of the test. I will go to 80 and see whether it goes to like about 10,000 cycles. And if it goes like 50,000 cycles, then I'll do another one at 70 and then another one at 60 and find out all the variants of the way the stress works. And then after I have the basic one from 90 to 50%, I'll start filling up the curve between them and try having a curve from 90% to 50% with like 10 to 15 samples so that I can have a smooth SN curve, which gives me an idea how the fatigue, it gives me a mathematical, almost a mathematical model of how fatigue works in that material with respect to stress. So I'll go back to the slides and I can show you what I mean by that. So depending on what stress range I'm working in, depending on what mean stress and environment that I'm testing, I would know exactly how the crack is going to initiate and grow in the material. If everything is going to happen in lab air, the effect of environment is not that much, except that you're doing a high temperature test or something like that. The effect of temperature in terms of a lab environment is not that much, or lab effect of environment in terms of lab environment is not that much. So this is what I meant by it. So I would start something at 80, 90%, and if it's less than 10 power 4 cycles, uh, because I for high cycle fatigue I need stuff from 10 power 4 and above. So if 90% is at 8,000 cycles, which is less than 10,000, I would do another one at this, which is 80%, and then 70%, then 60, and then 50. So I would know that 50 and 60 might all both be 10 million cycles. So I know that the values anything below 60%, it is going to have unlimited life in the material. So if that's the case, then I would start doing 62, 65, 72, 82, all these things for me to understand the entire growth. And the graph would finally look something like this, where I'll have very low life at high, and as I reduce the life it keeps going down, and then at one point it will flatten out, and that flattening out tells me that this material is a mild steel, or a steel which has, or a BCC material which has lower hardness and good strength, and therefore these are the reasons why you have anything that you see in a fatigue curve and it has an arrow mark next to it, that means that sample didn't fail, and that is at 10 power 7 cycles mostly. That's when they stop it. uh, and so you have flattening that is happening, and then you know that that's the point at which 60 ksi is your endurance limit for that material. The same thing can happen. So this is for steel. So any high strength material, high strength steel, or any high strength materials, and every face-centered cubic material, it is not going to flatten out. It is just going to keep reducing with stress applied. So as you reduce the stress, the life keeps going up. but there is not going to be a flattening point where the saturation happens in the fatigue life of the material. So by just looking at the uh, fatigue curve, we can actually say whether they are talking about BCC material or FCC material. Uh, there are a few high strength steels that can have the same properties like a mild steel. Sorry, properties like aluminum alloy, but that's a very few options. So the reason why I'm saying this is companies like GE, Rolls Royce, if they are presenting in a conference or they're publishing a data point, they're not going to say what material it is or what they're going to do with it, but they just show you a trend like this for a fatigue and with no numbers over here. It will be just stress and number of cycles to failure. So that's all it will have. And if it has a flattening, then you can guess what kind of a material it is. And if it just keeps going like this, then you would know what kind of a material they're talking about. Even though you don't know exactly what material it is, you can guess the family they are from, and then you would know most of the properties of the material. So a smooth, very important part of fatigue is that you have to make sure that the surface is smooth and in the gauge section at least, and there is no stress traces on the surface. And then the ASTM standard for fatigue test on metals is E468 that you're gonna use. You can use E466 too. It just depends on what kind of material and size that you're working with. The ASTM standards are, if you guys didn't know, is free for all of us. All you have to do is just Google ASTM Compass Akron, and you'll get the link to log in, and you can find out the different uh, ASTM standards. So this is a fully reversed cycling, so that means your R is equal to -1 cycling, and this is the data point for that material. So in this, a solid line tells you that it's a mild steel or any kind of a BCC material. The dotted line, when you see that there is no saturation happening and it just keeps reducing with stress, that's any FCC material or a high strength material. Reason why high strength materials acts the same is because of the addition that you have, the different, let's say, silicon carbide being added to material or carbon nanotubes added to aluminum. All these things are going to increase the strength of aluminum alloy, but it also makes sure that the material doesn't have much of any saturation happening in terms of fatigue strength, because all these spots where you have the carbon nanotubes or any fibers added to the material, all these points could be the point where your crack can initiate in the material. So once you have no, since you have no saturation happening, to find out what the fatigue strength is, for finding out the endurance limit or fatigue strength for a material which doesn't have saturation, is the stress at 10 power 7 cycles or 10 million cycles gives you the endurance limit of the material. That's what is expected. For most metals, 40% to 50% of its yield strength is the endurance limit for most metals. And So even if you don't do complete fatigue testing, if you are within 40% of its yield strength, it should survive for a long period of time. Uh, so that's, if there's a big table in the next slide, which is over here, you can, so for one series aluminum alloy, which is 99.8% aluminum and 0.2% copper and other junk added to it. I did talk to you about this a couple of days ago, and I said any of the pure materials are useless because pure materials are very soft and it doesn't have much of any give to it or any strength to it. Any load applied can shape them to any shape that is possible. So they have high ductility, but they will have very small strength for you to have use it for anything. So one series aluminum alloy has a yield strength of only 90 MPa, but you can for the same material, the stress at 10 per 7 cycles, which is the endurance limit, is almost the half of it. I said it doesn't need to be exactly, it is between 40% to 50% of the yield strength. And you can see for any material over here, it is going to be the same. 2024 aluminum is a little different. So that could be like something a little below the 40%, so it's around 30%. But that's just for the T3 temper. But a normal 2024 alloy with no heat treat will be almost, the strength also will be lower. The ultimate, sorry, I just have to go with this part, sorry. Would be a little lower, and you can have smaller amounts over here. Same thing with 7075. It has silicon in it, so it is a little lower, but it's still 33%, almost 33% of the endurance limit. So it's very close to 40. So you can say 30 to 50 if you want for aluminum. But if you can start saying for steel, it'll be closer than that, and half of its ultimate is perfect over here in terms of any. When you go to high strength, as you said before, high strength will start acting like aluminum alloys or FCC materials, so the endurance limit might be different. It won't be 50%, it will be around 30% for high strength steel. So, if you guys remember, know what quenching is, uh, so quenching is a process by which you're going to heat treat the material to a particular temperature, and then you're going to drop that material either in oil or some bath, um, and thereby what you're going to do is you're going to force, let's say, a molten steel or a knife that I have. I'm just dropping it, or I am trying to quench it in terms of an oil or something. This all these materials now are in molten state, so the atoms are agitated, but they are not melted and reformed to a particular shape. And I'm going to decrease the temperature from like 800 degrees centigrade to about 23 degrees for oil in like less than few seconds. Once I do that, you would see a lot of smoke coming off, and what happens is all these heat microstructure that you have is formed suddenly, and it what happens, it just forms like, if you guys have burnt a paper and you pour water in it, how does it look? When it's a burning paper and you pour water in it, it just forms like a crumble structure, right? That's the same thing that happens with steel. It forms a crumble structure, which is basically called as martensite. That the structure is over here like this, and that martensitic structure is the hardest microstructure that you can create in steel or any material, and thereby that material's uh, strength goes up really well. The tempering part is done to the material after it quenched. The reason why they do that is after becoming martensite, the material becomes really brittle, and you have to release all the residual stresses created on the surface of the material because of fast cooling the material. Uh, so what you do after that is you heat it up to uh, almost T line or T3 line, which is like 837 degrees centigrade or a little less than that, and then you start cooling them in air rather than cooling them inside. Annealing is cooling it inside the furnace. You're going to cool it in air, and thereby what you're going to do is you're going to reclaim the reduce the residual stresses in the material, so you're going to regain some ductility in the material. And that's generally what is done for most materials. And if you can see, this is 4340. All of them are 4340 steels. but they're just changing the condition. First one is just annealed, so you can see the strength at 745, and then when they did it quenching and at the tempering at a lower temperature, the strength is still high in the material. And when you see the fatigue strength of the material is like 20% of it. The reason why is tempering at 200 degrees is not much. It's basically like one sixth almost a melting point. So you're not releasing all the residual stresses in the material. So the material is still hard. So till about so that when you fatigue a material like that, what happens is till about a particular point, the material will just fail at 10,000 cycles or 12,000 cycles and stuff like that. And at one point, suddenly, the material will start being survives 10 million cycles. The reason why is these materials, because of how hard it has become because of quenching, is any stress higher than a certain limit, it is going to initiate a crack. If it doesn't initiate a crack, it'll survive for a lifetime. But if it initiates a crack, it's going to fail. So that's why you have a very low endurance limit for these materials. But when you test it at 450 MPa, let's say, you can can be sure that the failure won't happen. So that's the reason why lower temperature is bad. So let's say I do the same thing at a higher temperature, which is very close to one third of its melting point, or higher than one third, little lower than one half of its melting point. When I do that, I lose some strength in the material, but that's fine because I'm getting a higher endurance limit in the material. So I can use this material for my landing gears because of high stress that I'm going to have for impact landing. These materials can take it because the strength is higher. If I have this material which is quenched in tempered in a lower temperature, and I use that for landing gears, there's every chance of my material cracking and failing at a when it's used as a landing gear. So tempering temperature is very very important. Even the quenching helps to increase the strength of the material. And without quenching, you can see the strength is being at 745 degrees centigrade. So this is a very good way of understanding how important heat treat is to a material. And also there will be a chapter in which I'll be talking about carbon iron carbide diagram, uh, and that's very very important for you to understand what temperature you have to go. It's just a phase diagram where you understand what heat treat or what temperature is going to give you what kind of a microstructure for steel. So I'll be talking about that a little later, but this is the generic understanding of endurance limit. If the material is high strength aluminum or high strength steel, the endurance limit is 30% of the ultimate strength of the material. Whereas for any other material, if you don't have any other data with you, or you don't have enough material to do a fatigue test to understand the curve, you can assume that 40% of the ultimate strength would be the endurance limit of the material. If you are loading it only to about 35 to 40% of its endurance level, if it's ultimate strength, then the material should survive for a long period of time. If you plot a true stress amplitude with the number of cycles to failure, uh, this is generally for strain control testing or anything like that. Uh, you draw that and you create a curve. Let me see, stress amplitude versus number of reversals, so it's 2 times NF. So because every cycle you're going to reverse it twice the direction of loading. uh, because of that, the number of reversals is 2 times the life of the material, so it's 2NF. So when you're drawing something like this, you will see uh, two curves joining like this. And basically the two curves is like, one is your elastic strain, uh, and another one is your plastic strain curve. So because of your plastic strain and because of your elastic strain, how it turns, and that can be mathematically written as this curve over here, where this is how you get your Baskin exponent for your equations, um, and this is done for from low cycle fatigue testing of materials, and we'll talk about it later. But this is generally what is done for finding out the Baskin equations and everything. Baskin equation, Coffin Mason equation, all those things they start with the Baskin exponent that you can find over here. And for most metals, it is between 0.05 to 0.12. So we'll talk about it in more details later, but it's just one example of how mathematically we can explain the curves that is happening in fatigue. This is just an example from one of my papers that it is on landing gear materials. This is the material that is used for landing gears right now, more commonly, sorry, till about uh, mid 2000s, so 2005, 2006. This was the major material. So 300M is nothing but vacuum or remelted 4340 steel. So it's the same 4340 steel used for landing gears, but it is all processed, secondary processed in vacuum. So there is no chance of any inclusions of any gas happening, and everything is controlled in a vacuum. So it has a 300 ksi strength. That's why it's called 300M. M is basically the type of heat treat. It's quenched and tempered. So you have a mar tempering heat treat or microstructure. So that's basically what is called 300M. Uh, and you have 300 ksi, which is double than what of just an annealed material. So AM at 100 is a little different from 300M. Again, it is machined or it is processed in VAR, vacuum arc remelting, and it has the same 0.4% carbon in it, but it has other things, and the processing makes it a little different. That this material actually has a little less than strengthen this, basically like 260 270 ksi strength, but this material has like a 20 to 25% ductility in there, so it won't crash. If in a sudden loading condition, it will plastically deform rather than having a disastrous failure. So that was the major difference. So even though when you see here, um, the endurance limit is way higher, 1200 MPa over here, and the materials over here is going to be uh, way lower at 650, 550, or 600. So it is half of what it is shown over here. So that's the major difference between the two. But again, as I said, air at 100 is not going to deform by fracture. It is going to deform and still work, but then you have to replace it after it plastically deforms. So that's the biggest difference between the two. And Armat 100 is used now along with another material called Pyrovare 290. The 290 means it has a 290 KSI strength. And it is between these two materials, and it has this strength, almost this strength and almost this ductility in that material. And this is the material that I worked with, and that's the one that is used in the helicopters right now. Uh, Mean stress effects on fatigue life. I'll stop here because it's at 7:45 already, and I'll talk about the rest later in the class on Wednesday. Do you guys have any questions? I did throw a lot of information, I know, but if you have any questions, you can always ask me, and I'll tell you whatever I know. If you guys don't have any questions, I will see you guys on Wednesday.
Thank you.